Alright, so let's now learn about the empirical rules. And so now to get started, let me introduce a problem that gives rise to the idea of the empirical rule. So let's all have a look at problem number 1 right here. So problem number 1 refers back to that data 1 that we have been working with. And so problem number 1 here is asking what percent of data in data 1 falls between 63.8 and 88.8. So now let's have a look at data 1. So data 1 is here in front of us, and remember we're looking for those data values that being between 63.8 and 88.8. And so since we still have the data here, we can quickly count that between 63.8 and 88.8, these values that I'm about to highlight right here, they're all between 63.8 and 88.8. So those are all the values that qualified the question. So once again, let's get back to and read the question a little further. And so now as we are now reading the question again, the question is asking what percent of data from data 1, and I did make a highlight like that. So what percent of data 1 falls between 63.8 and 88.8? And so the key idea here is we're looking for as the percent of data, and data 1 is just the data as an example we're working with. But then another key idea here is that we want those values to be 63.8 and 88.8. And that was the reason why a moment ago I was looking at data 1 and I was highlighting those values that qualify being into this interval of values. And there's the low and there's the high here. Let's have another look at data 1, where the highlighted area here highlights those values as the physical counts that falls into the requirement. Those values are those that fall between 63.8 and 88.8. And now let's get over to my working board here, my writing board. So as you now have seen in the data and had a close look at the question, then finding the answer to this question or this problem is not challenging at all. Quickly we can count that there are 34 of those data values being in a highlighted area, indicating they satisfy falling into that interval. And we divide by the famous n number of data 1. So finding a percentage for any of us here is a simple work. So 34 of those values fall between the interval, and we're dividing that by 40. And then this ratio over here, or this fraction, is going to be multiplied by 100%, and that's how we are going to get our answer. Because remember, the answer was looking for what percent of data in data 1 falls between that interval designated. And so the calculation here turns out to be 85%. And so now, as we finished finding that percentage, now I have to tell everybody that getting that percentage is not really the main intention of this entire problem. Now, it's easy that we can find 34 the values in this data 1 out of 40 and turning that into an 85%. But let's have a closer look, because the real intention of this question hasn't been unlocked yet. Now, let's have a closer look at the two lower limits and the upper limits here, the lower end and the upper end of that interval. So 63.8 and 88.8. A reminder, maybe I can put it on a side note here, but a reminder that in data 1 we already have found throughout learning lectures previously that mean value of data 1 is equals to 76.3, and standard deviation of data 1 was calculated to be 12.5. And so, to tell the truth now, these two, the low and the high of this interval given in a problem, did not really come out of nowhere. They are a special interval, special pair of low and high right here. So let me now bring up that truth right here. I brought up the reminder about that the mean value and the standard deviation of your data 1. So if you're looking at this low end right here and combine together with your understanding in terms of having the mean already available and having the standard deviation, then it looks like 63.8 is indeed from where the mean is 76.3, and simply subtract 12.5 right there. That's how we can simply get the 63.8, and that's give me a 12.5. So the difference between 76.3 and the 12.5, and that 12.5 right there gives me the 63.8. So if now if you look over to the other end of the interval, the high end of the interval, that value 88.8, once again I have to tell you that truth, that 88.8 is really 76.3 plus 12.5. So what I brought up here is that this value, another way of saying that this value here, it looks like we subtract a standard deviation. So remember, I brought up the standard deviation here being 12.5. So here I'm treating a 12.5 as one standard deviation. And so 76.3 subtract one time. So this is right now one standard deviation. But what we did here is from where 76.3 we subtract one standard deviation from the mean value, and we obtain the low end of the interval. Similarly, this high end of the interval was, as I pointed out, was obtained by, this is the mean of the data, but then we simply just add one standard deviation. So this is one standard deviation. So another name at this point, as we gradually see more truth and more truth about these two numbers, the low and the high right here, then now I can start using that term. This upper or the high end of the interval over here is regard to that this value 88.8 in particular is being in the way how it is from where mean was, we plus one standard deviation. And so here I'm saying that I am one standard deviation above this value 88.8. And then of course at this point, if you start having some connection in mind regarding what we have learned previously, it will all be connected. This other value 63.8, in other words, looking at the way how the math was done right here, simply to obtain that 63.8, once again I repeat, from where the mean was being 76.3, I simply subtract one time of the standard deviation, and I ended up with 63.8. So in other words, I can say that due to that subtraction nature right there, then 63.8 came out as being the value that's one standard deviation. So I'm calling that 1s to indicate one standard deviation. So here I am one standard deviation, but below mean. So now back to what I said earlier about how special this interval from the low end to the high end is. Let me put them all together here. But the low end of the interval starts from 63.8, and the high end here ended at 88.8. So here's an interval in traditional format where we show the low and the high with a comma between. But this interval now, as I have been explaining, then here's another way how we can see that. I can now say that this interval is the interval of values. The important term I would like to introduce here, the interval of values within one standard deviation from the mean value. And so let me clarify, but within one standard deviation from mean right here, what I mean here is you can imagine there's a lineup number, and the way how this interval is now is that the 76, or the mean value in general, the 76.3 is right in the center, exactly in the middle. And the low end and the high end are exactly symmetric, right around it, where the low end 63.8 is here, and up to as high as 88.8. But all that from the beginning to the end, anywhere we are inside of that interval, the values are within one standard deviation away. Because this is one standard deviation above, and this is one standard deviation below. And that's once again what I meant by the interval from 63.8 to 88.8 is that interval of values within one standard deviation from mean. And then a lot of time for short, I can just call that it's the interval within one standard deviation from mean, for a shorter way of calling that. And so now, after understanding how special that interval being brought up is, now I have to start introducing, but a lot of time in statistics, we are facing that type of question, that kind of problem where we're looking for the interval of values, the interval of values that falls within one standard deviation from the mean. And later on, as we progress through the course, you're going to understand how important that kind of question is for a lot of people in many different careers out there. And so after that problem number one right here, let me now bring you into problem number two. And if you might notice that I haven't mentioned anything at all about the empirical rule, but let's have a look at problem number two. So problem number two, now let's say we have a data and now we're done with data one. So this is a completely different problem. We are regarding to a completely different data here. So our data here is about the 2-month-old baby weights right here. So let's go ahead and read together. So now this problem number two say 2-month-old baby weights are on a normal distribution. So for now, we can put aside this information right here, not to worry about it. But say this data is on a normal distribution with average 12.3 pounds. So you can imagine that we got generations of babies, and anytime that they hit 2 months old, parents bring them into a medical facility for measuring their weight. And so this average here came out from a lot of babies. And this average here, some computer, some measuring device did a calculation and gave us this value here. So for now, we don't need to worry about the validity of this value, but instead let's take that as something that's already truthful, and then it's the average given to us right here. So we have a value, an average value already calculated. And furthermore, we have a standard deviation being 0.75 pounds. So how valid, how truthful these values are is not the main aim of this problem, but our main aim here is for now is to make use of these given information, and let's answer the question here. So at the end of my first paragraph right here, then it's just simply a description of my data. So in problem two, we have a completely different data outside of data one, and that's all about all of the description of data we have here. And so now if we look into that question right here, the question regarding this data starts here. What percent of 2-month-old baby weights? So all of a sudden it starts bringing up that kind of similarity with the earlier question in the problem one we have previously looked at. So let's complete reading the question here. What percent of 2-month-old baby weight that falls between 11.55 and 13.05? And so as soon as we finish reading the question, we can immediately recognize there are quite a few similarities between this question being brought up here to us and the question that was brought up earlier in problem 1 here. The main idea here is that there is a given interval. There's a low end right here, and there's a high end. And what we are doing here primarily is that we are looking for what percent of that data. The data we're looking here is no longer data 1. The data we're looking here is the data that has all of those 2-month-old baby weights. But still, we're looking for that percent of data that falls between this designated interval. And then we can further work around a little bit. Let's find out that, hey, the mean value in this data has mean value being 12.3. And the standard deviation is also given as 0.75. So the low end of the interval, and I'm not really trying to promote any new technique or anything yet, but at least some similarity already happened with that same question back in that problem 1. So why don't we do the similar work to recognize something that's relate between the low end, the high end to those right here. But so now experience now telling us that 11.55 is exactly 12.3 from where the mean is. Subtract 1 time of the 0.75, and I carefully said subtract 1 time of the 0.75, even though traditionally we don't need to write down 1 times 0.75. But so once again, what we recognize here is that this is the mean of the data, and this low end value is simply being obtained by subtracting 1 standard deviation from the mean value. And so I am now going to look over to the other value, the upper end of our given interval, 13.05, and let's find out just for curiosity. 13.05 does turn out to be 0.75 added to 12.3. And so again we recognize, wait a minute, this 12.3 is again the mean value of the data that we're currently working with, and plus with 1 standard deviation. And so in other words, here we run into that kind of interval again. Now I can say that I can make my conclusion that 11.55 to 13.05, anywhere in that interval, is the interval again, right? The interval of values within 1 standard deviation from the mean. That's the general idea about these kind of intervals given to us up to this point twice. But so we now realize the truthful nature of this interval, it's being the interval taking values within 1 standard deviation from the mean. But so what? We haven't found the answer to our question. Once again, back to my the slides up here on the board, and then the question has stated that what percent of 2-month-old baby weights that falls between 11.55 and 13.05? We haven't found that answer. So if we attempt to carry out a work similar to problem 1, it's going to be a failure this time. We are going to fail. We're going to fail to find the answer. As soon as I finish writing this down, I want everybody to take about maybe 1 minute, 2 minutes, pause the video and think of the reason why we actually failed to find the answer in this problem, even though the question being brought up here is exactly the same. So go ahead and have some thinking about that. All right, so I hope everybody had some good thought about that and starting to be convinced about why we're going to fail finding the answer here. I kind of told you ahead, but here's the reason why. Don't you realize that if we're looking back into this data, everything from beginning to the end of the data description, all it told us was that we're looking at a data with 2-month-old baby weights. Now this plural right here that I'm catching that caught my attention are actually quite dangerous. It is indicating that we're having a lot of 2-month-old baby weight measurements. However, did it tell us how many? It did not, obviously. What I'm trying to point out here is that we did not have the n number for this data. Now, the work we did to answer the exact same question in problem 1, what we did was we got the count, 34. If I remind everybody about problem 1, we made a count because we saw the list of data 1. We put that over 40 being the end count, and so for that, the answer, getting the answer is easy. But in this problem, where's the count? We actually don't know the count. And as a matter of fact, we're beginning of our quarter not too long ago, so I don't want to rush anybody into in your learning. However, the idea of working with gigantic data where we have to ignore the end count is the idea that's waiting for us as we progress through the quarter over here. So here it's just a sort of like a first preview of what's going on in the future for our quarter here. But so now, since we don't have an end count, just imagine that here we have a real big data, the kind of big data that nobody would like to know, how many 2-month-old babies out there. Because seriously, I'm talking about generations of babies. Look at the medical records of all those medical facilities. They're having not only one generation, they have many generations of babies. And so it's hopeless to look for that end count, and it's pointless to look for that end count. So all we need to keep in mind here is we have a very big, gigantic data where we already had a mean. So maybe we're lucky enough that we have some super powerful computer that handle the mean calculation for us. So we got the mean being 12.3, and we got the standard deviation being 0.75. But now, in order to find the answer to this question, we have to use a different method right here. Aside from the traditional, get the count and divide by the n number and multiply by 100. All right, so now everybody is really ready to understand what the empirical rule is all about. It's actually not only one rule, it's a set of rules. So really now we get into the real core of the empirical rule. Right? But before we can really get far on the empirical rules, I must point out that the empirical rules is only valid, meaning it's only working for data that is on a bell curve. We actually have seen that term. It's data that is on a bell curve is another name for that is we're working on the normal distribution. And there are still a huge amount of understanding regarding the normal distribution. Here I'm simply only lecture in this I'm only going to deliver my lecture in this topic as a preview to the world of working with the bell curve like that. But yes, the bell curve is another name, the formal name is the normal distribution. So let's have a look over to my prepared normal distribution bell curve right here. And you have seen that a normal distribution is simply one among the many different distribution shapes that exist out there. So imagine that after you build a histogram, then inside of this nice looking bell curve right here, then this is all of histograms, a whole bunch of histogram bars are being located in here. And for now, please, you don't need to worry about what these lines are all about yet. So maybe I can quickly hide them away so that it's not going to be too interfering with your attention yet, and then we will put those little lines back later. But so now we very briefly talked about, you see, remember that mean values, medians, and mode, there are different types of center depending on different kinds of distribution shapes out there. But now when we're on that special curve right here, and I also briefly mentioned about that, but when we're on a special curve like this one, nicely symmetric, where the amount of data is fading equally on the two sides right here. See, my mouse movement right here is trying to indicate that as we're moving further away from that nice clear center right here, then the amount of data being faded away, being less and less to the two ends of the data. And I'm not saying that this distribution shape is going to stop right here. It's just the boundary of my screen that it can allow right there, but it can go further than that. And for now, even you don't even need to worry about what these numbers are here yet. But so the bell curve here, connecting back to what we have learned, then this is where mode is here, mean is here, and median is also here. So let me quickly make a re-sketch of that on my working board over here. But so now when you're on a bell curve, anytime you're on a bell curve, then I generally explained earlier that when you're on a bell curve, you don't need to worry anymore about we got three different types of center because they're all at one place. Mean is here. The reason median is here as well because see, all that shading area inside of this curve. Now, so here on my working board, and I can actually shade the area inside. And the area inside right here, what you can imagine is these are histograms, a lot of histogram bars, to the point that we don't want to really see them one by one anymore. We just imagine that, hey, we got a lot of histogram bars, so the whole area cumulatively is the area representing 100% of all data. So all that area here being shaded is 100% of area. And so that connects with the concept of median, because remember back then we studied that median is a cutting value that divides the area into two equal halves. So isn't it perfectly convincing that median is right here? Because since our shape is perfectly symmetric right here, then this, where I just now call the mean, but now can also we realize that it's the cutting value where it divides the area here, divide the amount of shading, the amount of data graphically here is the shading into two equal halves. So there is a 50% here that we can easily recognize, and there's another 50% here that we can recognize as well. So mean and median is the same spot. And now the high peak nature, there's only one high peak throughout the entire distribution shape. And so it makes perfect sense that mode is also likely here. And that's the reason why, and later on at some point, starting at about the middle of our quarter, we're going to turn all of our focus into studying all the other nice properties of the normal distribution. But for here, once again, we only need to look on a very brief preview surface understanding of that. All right, so back to my animation and back to my prepared graphical bell curve here on the computer screen. Then so you see, the reason I put a 0 here is to indicate those values that stays right on mean. Remember we talked a little bit about z-score, that's what it is. So if any value that stays right on the mean value, that represents as z-score being 0. But then I'm not even too worried about that. Or another way of thinking is that you at 0 standard deviation away from mean, which is mean is right here. And then median is here, mode is here. And so now I'm going to start putting up the other lines here again. I'm going to put those other lines back. And so it's not important to worry about how far on this picture. So scaling is not really the important point here. But so it's just a choice I made here in my picture. But let's say one standard deviation value is about equal this big, this much on this line right here. If you say so, and let it be, then so another distance like that out is one more standard deviation. So what I'm trying to say here is that these lines is to represent from where this middle line is, the distance from here to here, that is representing one standard deviation. So think about if we're right here on mean, then going to the right and hits right at that value x, that value equals 1 right there, then we're at 1 standard deviation above mean. And so once again, on this bell curve, the mean is here. If we're looking back into being hitting right at that -1 right here, it's indicating that from where the mean is, we are, and you can see that there's a negative here, we are 1 standard deviation below mean. And so now, if we now think back about those questions, which is actually one question, the question in the two problems I brought up right there, what percent of data falls within 1 standard deviation? So it's starting of our journey here, but a lot of time, graphically speaking, the percent of data, the percent of values, the percent of data is represented on the bell curve as a graphical shading. So here, that's why I'm putting a shade up here. But this total blue shaded area here is to represent the amount, the percent of data within 1 standard deviation. So you can see that graphically displayed, this is from where it's 1 standard deviation below mean to, and these are all values between. So the amount of values here, but the line here is representing those, these are the values between -1 and 1. So between 1 standard deviation below mean up to 1 standard deviation above mean. Okay, and so now back to my working board right here, and we have to start writing down the rules right here. But the empirical rule states that anytime you're on a bell curve, there are, rule number 1, there are about 68% of data values falls within 1 standard deviation of the mean. And so this statement for now is a statement that was previously proven, and you will find the answer to why it's concluded to be 68% in the next couple of weeks as we progress through the quarter. But for now, let's take that as a previously proven result right here. So it's a statement now. Say, let's turn our focus back to the animation, the bell curve here on my screen. But see, so now what it says here is that on this bell curve, if you were shading the entire area from wherever the tiny tail here on the left all the way finishing out to the tiny tail on the right, all that there is 100% of data, or just like how I drew on my writing board earlier. But now this interval is not to cover the entire bell curve data. It's only cover the amount of data from 1 standard deviation below to 1 standard deviation above mean. So now, just now we learned that the empirical rule stated that this shading area compared to the whole curve, it takes 68%, or in other words, there are 68% of data being contained inside of that interval from anywhere from 1 standard deviation below mean to 1 standard deviation above mean. And so now, as you start seeing that through the picture, and I also write it down on my writing here, then let's look back into our problem. The problem number 2 that we were unable earlier, we were unable to find an answer. But now let's have a look at that one more time before we completely be done with that. So here's our problem 2 that we were unable to find an answer for earlier. And so now if we can now start making use of that piece of information here where it says 2-month-old baby weight or on a normal distribution. Now at this point, this highlighted information start making sense, because what we just now learned is that the empirical rules, before I stated the rules right there, I did clearly mentioned that the empirical rules only work or only valid when you're working on a normal distribution. So in this case, you don't need to find out, you don't need to worry about how this data was known to be on a normal distribution. Let's say it was already verified that somebody else have done histograms and put up a whole bunch of histogram bars and came back to us and saying that, hey, this data is now known to be on a normal distribution or a bell curve. So as long as you know you're on a bell curve, then finding the answer to this question is easy. Remind yourself again, this interval is that interval on my board here. We made that conclusion earlier. The interval between or anywhere from negative 11.55 to 13.05 is the interval within 1 standard deviation from mean. And so, perfect. The empirical rules now is just simply telling me that we're on a bell curve and we're within 1 standard deviation from mean. The answer now is just straight old 68%. Without any worry about what was the calculation for this. We don't need to do that here yet. But we just simply apply the empirical rule. And momentarily looking back into that problem number one more time, we're starting to worry. But wait a minute, the exact same question here, but when we brought that up in problem 1, how come the count there was a little way too high compared to what we just found here and concluded here? So in problem 2, the exact same question, but the answer was only 68%. But in problem 1, the exact same kind of question being brought up there, the answer was actually 85, if everybody remember. And so the reason for that was, if we notice, data 1 that we have been working with has never been told to be on a bell curve. As a matter of fact, we already built data 1's histogram. It was a short, small data, and let's look back at my writing board right here. But let me remind everybody about the histogram of our data 1. It kind of looked like this. There's a column, and then there's a higher column. Then it goes lower and really lower, and kind of die out, and then resurface. So the histogram for data 1 right here, and you can quickly reconstruct it. But the picture itself, even though a pretty small data, can already tell that it's not a normal distribution bell curve. And so that is perfectly the reason why the answer, the 68% coming out from the empirical rule, just not going to work out on a data distribution like this one. So luckily that we had an actual n count, and we can actually count through the data to come up with 85%. But that explains why the two answers were so different from what we found in problem 2 and what we found in problem 1. All right, and so now back to my bell curve demonstration on the screen right here, on the computer screen right here. Then we're gonna start wonder, hey, if we had a rule, if there was a rule stating that there are 68% of data being inside of this interval, once again from negative 1 or from 1 standard deviation below mean to 1 standard deviation above mean, then is there another rule for that longer interval? So here I'm talking about a longer interval, and the interval is admittedly twice as long, but I'm only saying twice as long. But do not assume that the amount of data shaded inside here is going to be twice as much. So let me bring up the picture. But yes, there will be an answer to that. What about we are in the interval from 2 standard deviations below to 2 standard deviations above right here, and that's being described by our picture. And notice it's not exact. It's not really twice of the 68 amount. And so back into my writing board. So now once again we're on a bell curve, and as long as you're on a bell curve, it is guaranteed that there are. So now statement number 2 of the empirical rule. It says there are about 95% of data values on a bell curve that falls but here it's also a new term, so to allow me to write it in red ink right here, but that falls within 2 standard deviations. from or of mean value. And then one more time, as we're looking into the picture of this the bell curve prepared on my computer screen right here, then if I pull up that area being anywhere from 3 standard deviations below mean to 3 standard deviation above mean, then we're going to have another statement here. So here's the area. First of all, let me show everybody. So that area now is almost cover the entire curve. I'm talking, and like I said again, shading area here represent the amount of data. So now you can see that as we go from 3 standard deviation below mean to 3 standard deviation above mean, we cover almost everything. Now my eye can still tell a little bit of white here, but that's really small right here. So that kind of brings up an understanding that, you know, when we're inside of the interval of 3 standard deviations, we almost finish the entire curve. We almost cover the entire curve right here. And so back into my writing board right here, then yes, when we're on a bell curve, there are about 99.7% of data value that falls within 3 standard deviations of the mean. Alright, so now let's look at some further developments of the empirical rules. And let's get back to my bell curve on the computer screen here. And so we have learned that so on a bell curve, mean value is right in the middle of the bell curve. Mean value of the data is right in the middle of the bell curve right here, that nice center line. And so these lines are here indicating being 1 standard deviation above, and here is 1 standard deviation below the mean, and this is 1 standard deviation above mean. And so we've learned previously that this area represents the amount, the percentage, the amount of data that's being within 1 standard deviation. So you can see that it's 1 standard deviation from mean on either side right here. So this data, this shaded area represents that percentage. And so we've learned that this shaded area here is 68% according to the empirical rule. And so the question now is that, what if we have an area like that? And so you can see that the change in my picture here, that immediately that area got cut into the exact just halfway, and your eyes can see it. First of all, what should have caught any of our attention here is that the bell curve itself is very symmetric, where that nice mean value is right in the middle, and so everything is symmetric right about the mean value, right about that center line right here. And so now that complete full 98, and that complete full 68% there previously, now seems like it got cut off into only half of that. And so this area here represents the amount of data that falls between the mean and 1 standard deviation above. And so similarly, from that same 68% of data shaded here, the other area to the other side can also be argued the same way. So what that is here, once again, strictly taking advantage of the symmetric nature of the bell curve, then this area here on the other side of the nice center is going to be again half of the 68. So on my writing board now, so here's that similar bell curve again on paper. And so as a recap of what we were looking at, then this area that I'm drawing only happening between the mean and 1 standard deviation above to obtain that area. The quick math we do in here is a 68%, but divided by 2, and so it's a 34%. And then similarly for the other area over here, this other area that I'm drawing here between mean and 1 standard deviation below, this area is also another 68%, because the 68 is the complete interval from -1 to 1. So 68% divided by 2, that is another 34%. Sorry for the backward writing, but I just want to show, reinforce the fact that things are all quite symmetric here. And so this area here is 34, and this area here is 34, and we just did a quick little math for that. All right, and a further details, a further development here can be found in this kind of problem. So let's say we're on a nice bell curve again, a normal distribution, and this line right here is indicating we're 1 standard deviation above mean, and this other line here is indicating we are 2 standard deviations above mean. And so the area shaded here is indicating the percentage of data, the percentage of value that's being anywhere from 1 standard deviation above to 2 standard deviation above. So the interval is the interval of values, but the percentage once again represents the amount of data being inside of that interval. And so according to the nature of the bell curve, and this is how we can use the empirical rules to find out further developments right here. But this interval right here, we have a way to find how much data being contained in there. All right, so let's start out with this area right here. Now, this area on the bell curve, it goes right from the mean to 2 standard deviations above. So this area, in other words, came out from, it has 2 standard deviations away from the mean value. And so to find this area, we can think about having that the total area stated from the empirical rule, that if we are inside of that 2 standard deviations interval, anywhere from 2 standard deviations below to 2 standard deviations above, this area takes 95% of the entire curve right here. So 95% of data being located inside of this. And so back to the area we were looking at earlier. So this area right here must be the area shaded between here to here. It has to be in similar kind of problem we have seen in the earlier development. 95%, but being cut it in half. So that calculation gives it being 47.5. So then, getting to this actual area that we were aiming at here, then this area, one way of thinking of that, it came out from, think about that 47.5 amount of area again. This area was 47.5% of data. But now I'm going to take away that area from here to here. So do a quick little math right here, and we recall that this little amount of area from here to here is right from mean to 1 standard deviation. That amount of area was 34%. And so that means to find this, and my animation hopefully reveals the way how it's done right here. Our total area from mean to 2 standard deviation was 47.5. But now we take away the empty area being white out right here, is 34% being taken out, being whited out. And so the amount left right here makes sense to be, so now that amount on my writing board here, that amount, now we can express the math here, 47.5%, but take away 34. So remind yourself that 34 was in here between the mean and 1 standard deviation away. And so this area being shaded now has to be a 13.5%. And then pretty much the exact argument can be made again on the opposite, on the other side on the bell curve. So now this amount of area here from 0 to 2 standard deviation below mean, once again, it's half of the 95% according to the empirical rules, because the empirical rule once again say if we're looking at that interval from 2 standard deviations below mean to 2 standard deviations above mean, this interval is 95%, and that's all the empirical rule said. But now we can imply further that half of that, which is only halfway of the interval from -2 to 0, this interval here, now the shaded area is covering 47.5. It's 95 divided by 2. But then, relating with our work we've done earlier, then this, in that case, this area was exactly symmetric with the other area. And the way we're calculating that would be the similar argument. Think about the 47.5 is here, and take away the white area. The white area that just the white area that was just comes up right here. That was 34%, half of the 68. And so here, back on my writing board, this other area. Similar math, we go 47.5, subtract away 34%, because there's another 34% here. And so now clearly enough that this area is 13.5 on that area. All right, and to further develop a couple more ideas on the empirical rules. So let's look at this area here. And so the shading area, the shaded part is starting to get a little small and hard to read, but what you look at here is the shaded area, the area shaded between 2 standard deviation above mean to 3 standard deviation above mean. So you can see that the center of the bell curve, the center line of the bell curve is here, where the mean value is right here at. But the shading area we're looking at keep getting further out and further out, and so they're getting smaller and smaller. And so, and then the way we're doing here is going to be similar for the other area right on the opposite side. So here there will be another equal amount of area being from -2 to -3, being from 2 standard deviations below mean to 3 standard deviations below mean. Okay. So now let's see some arguments of how we can come up with how big each of these area value is. So let's say go back to this area shaded between 2 standard deviations and 3 standard deviations above mean. Then how I see that is, once again, this total area is half of the 99.7%. The reason for that is, think about the empirical rule stated that all that area from -3 to 3, or there are about 99.7% of data being within 3 standard deviations of the mean value, meaning that interval from -3, or that interval from the 3 standard deviations below mean to 3 standard deviations above mean is going to take 99.7% of the bell curve. And so, and you can notice that there's still a little bit of white area above and below those two cutting points right there. And so now it makes sense that if I now white out half of that, so anywhere from always from the center anywhere to only one side, that's exactly half of whatever being stated from the empirical rule. And so this amount of area now has only, the math here says 99.7, but we cut that in half. So that's either how big that is here on this right hand side from the mean out to 3 standard deviations. there. And so that amount there, the math shows that it's 49.85%. And so think about our designated area that we were looking for. So once again, and the animation I did was just there. Think about the entire amount being 49.85, which is half side on the bell curve, counting from the mean out to 3 standard deviations away. And so I'm going to now take out or white out the amount of area from 0 to 2 standard deviations away. And so recall, and we did some math at this amount of area here that we just took out. The amount of area that we took out, this amount here was a 47.5 as a reminder. And so this amount we're looking at here is simply the 49.85, but take away. So in my math now, what I'm doing in the next step, $49.85, but subtract away 47.5. And that now equals, the calculation shows 2.35%. And so that would represent how much area being in that little portion. All right, and so the same argument, or at least the similar argument, can be made again, that this other area right here, anywhere between 3 standard deviations below mean up to 2 standard deviations above below mean. So this area here completely below mean right here, but the way how we argue it is going to be the same. Think about, so for that amount of area, think about where we had here, all the way from the center of the bell curve out to 3 standard deviations away. That was 49.85 as we showed in the math earlier. And then now we're going to subtract out some area, and the subtract out is going to leave the white area. So the white area being subtracted out here was that 47.5, so we're taking away 47.5, and our math work turns into calculation again, say 2.35 left over in this little area, happening anywhere between 3 standard deviations below mean to 2 standard deviations below mean. Alright, and so this little tiny tail right now, and even on the computer screens right in front of me, it's still a little hard to see that, but what we have here is the amount of area left that's staying above 3 standard deviations, or that other area. As you can see, there's another blue being shaded here, but that's indicating the amount of area, and you can see that it makes sense to be pretty tiny amount of area left being outside of that interval from 3 standard deviations below mean to 3 standard deviations above mean right here. And so how big is each of these little guys right here? And so at this point, combining all that understanding together, now I'm going to change my route of making my reasoning slightly differently a little bit. But let's think about, and we have learned enough experience that any one of these areas, my intention to point out is that anytime you're looking at one portion of the area on the right hand side on the bell curve from the mean value, then there's always another exact symmetric area, exact equal amount on the opposite side through the mean value line right here. And so in that way, let's quickly do a calculation slightly differently. So our aim here, and back on my writing board right here, our aim is to find either one of these little tiny tail area. But let's say, starting out to have, the reason I'm doing this is I just want to reinforce the fact that, and I also mentioned this earlier, that anytime you're inside a distribution curve, doesn't have to be a normal distribution. It could be whatever curve that is, but I'm talking about the amount of data inside any distribution curve has to be, makes sense to be 100%. And so 100%, meaning if we cover the entire amount of data inside a bell curve. But empirical rule says anywhere we between negative or anywhere we between 3 standard deviations below mean to 3 standard deviation above mean that amount of area here. I don't want to make too much shading, otherwise it's going to make the picture really hard to see. But that amount being contained inside my interval with the arrows here, that amount of area is 99.7% according to rule number 3 on the empirical rule. And so the two little tails together, the two little tails that we shaded here were being outside of the 99.7. They're not inside, they're outside. I have to emphasize that. And so being outside, the famous mathematics work to calculate things that outside of a group is to take the whole 100 and minus away the big group. And so subtracting away the big group, it leaves us a 0.3%. So keep in mind, I keep having students mistakenly take that 0.3% as each of these, but the 0.3 is the total outside of the center of the middle interval here. So 0.3 means both of these two tails together added up is a 0.3. So that means this little point area here, this little tiny tail here is only a 0.3%, but we've done that trick about 3 or 4 times now. So here's the next time we're doing it again. We cut that in half because it's only on one side of the bell curve. And so that gives me, the calculation shows it's going to be a 0.15% there. And same argument, or at least similar argument. 0.3 is the total amount outside of the 99.7 interval. But then we're going to cut that in half, and that gives me 0.15% in there only. So now each one of these little guy has a 0.15% or 0.15% area. All right, and so now we're ready to make a final conclusion of all of these right here. The entire bell curve is supposedly 100%. So 100% of data totally inside. So keep that in mind. So since empirical rule sets anywhere from 1 standard deviation below mean to 1 standard deviation above mean was 68% data in there, and so now we have proven previously that this amount of area I'm shading here, that's, now let me make a label, 34%. And so similarly this other exactly symmetric area over here from the center out to 1 standard deviation below me, this is another 34%. And once again, think about how it's consistent with the empirical rule is that if we're adding these two areas together, we have a total area, which is the amount of area stated in the empirical rule, being 34 plus 34, 68%. And then we spent some time finding out how big that area is. That now I'm shading a little differently here, but this area from 1 standard deviation above mean to 2 standard deviations above mean, and then we have an equivalent versions on the opposite side. So these two, each one of these, that one there is a 13.5, and this little area there is another 13.5 there. And so let's double check again. If we're now adding up all the little areas being shaded here, the 13.5 plus 34 plus 34 plus 13.5, we do end up with a total from here to here again. That is a total of 95%. And once again, the length I'm indicating here is the length of the interval, but the percentage here I'm drawing is the percentage of how much area shaded inside of that length. And so it takes 95%. And once again, it comes back and agrees with the empirical rules. Here we're just learning how we can chop that into small portions, because once we understand these little areas right here, it's going to help us into doing a lot of other math work right here on the bell curve. And so we further found that this little area that happens between 2 standard deviation and 3 standard deviations above mean right here, this area, and also having an equivalent versions, but on the exact opposite side right here. So each of those guys takes only a 2.35%. So there's another 2.35% here. And then now the cut that's giving 3 standard deviation below mean to 3 standard deviations above mean right here. Think about that once again. If we're adding all of these little amount of areas together, 2.35 plus 13.5 plus 34 and plus 34 again plus 13.5 plus 2.35, that total interval, that long lengthy interval from 3 standard deviations below to 3 standard deviations above, and all of that amount of area added together, we get back to a 99.7%, which was stated in the empirical rule. And so each of these little guys out here, completely outside of the 3 standard deviations interval, each of these guys right here, we already calculated that each of those is a 0.15%, and here's another 0.15%. It's a pretty small amount of data. 0.15%. Right, and so now if we really are adding up all of these little pieces together, then that gives us a 100% of area being totally inside of your bell curve data, of your normal distribution data.